Hi, everyone. So you're here to hear about, hopefully, patterns, challenges, best practices for supporting pipelines. Clicker is not working. I'm Rita Sodt. I've worked for over 5 years on an ads SRE team in Seattle, supporting Google Analytics pipeline primarily. And I have a passion for monitoring, especially pipelines, and solutions that work across a variety of complex systems. As of 2 months ago, I moved to Zurich, and I now work on a monitoring team, part of whose goal is to work for pipeline. This talk goes well beyond my own experience, though, drawing on best practices and patterns shared from a diverse set of teams running pipelines throughout Google that gather periodically as a pipeline working group to share these things. So many thanks to all those that have contributed and taught me what I'm about to share with you today. By a show of hands, how many here support a data processing pipeline? Okay, yeah, and how many are paged when something goes wrong with this pipeline? Okay. Are there other pipelines in your system that maybe are supported by a different team, like a dev team, or have not been onboarded to SRE? Okay, well, yeah. So, okay, that's good to get a sense of that. How many of here, if you didn't raise your hand, that you work on a pipeline, work on a system that will break if there's an underlying data issue? And does that data get there via pipeline? Yeah. Okay, so I think part of why I think pipelines is important is even if you're not on a pipeline team or a pipeline SRE, if you are doing anything with data, there's a good chance that some pipeline downstream or upstream got it there or didn't get it there. I think there's room for SRE for managing pipelines, both to improve the reliability and speed up development velocity safely of pipelines. So, topics. So first we'll hear about what are pipelines, kind of what makes them unique, and how are they different from serving systems? What type of trade-offs do we make when we're a team supporting pipelines? And I might go quite quickly since there's a lot of content, but I'd love to chat after the talk, so even if you don't ask a question, come find me in the hallway. Then we'll cover failure modes and how to respond to them, the sorts of tools and instrumentation that make you effective during incident response for a pipeline issue. We'll talk about how to alert yourself so you detect issues in time to stay within an SLO and keep your users happy. And we'll talk about what an SLO even is for pipelines and how to measure. Then maybe my favorite part of the talk, but kind of the hardest in some ways, is how to prevent outages, how to do speedy development of pipelines with safe releases, healthy development lifecycle. Sometimes overlooked by SRE, but I think a very important part. So what are pipelines? Let's say you have a complex system. At the very tip of the iceberg is everything the user can see, everything that they interact with. Underneath is a potentially much larger part of the system the user knows nothing about. It's powering the product by delivering data, maybe processing events, web or mobile interactions, generating reports or novel stats that are surfaced to the user or business. So underneath that tip of the iceberg, this is where many of the pipelines in our systems lie. Distant parts of the systems might be dependent on each other, and a pipeline whose data output a serving job depends on could bring down the whole system as far as the user is concerned. So a pipeline like this one, whose goal is to assemble a car, can be composed of multiple stages, where each stage performs some task on what it was given from the previous stage. One stage here is to put the door on and the wheels and so on, and the end result is to take a bunch of pieces of metal and turn it into a car that people can drive. If any stage is done wrong, it could jeopardize the viability of the car. If any stage takes too long, it could cause a bottleneck that makes it longer until the user can drive. Pipelines like this also have state. It's not time to put the hood on, maybe if the engine hasn't already been added. So similar things apply to maybe you can think of a pipeline that in one of your systems today. I'll talk a bit about pipelines versus serving jobs. So a pipeline can resemble an assembly line you saw where the data flows through the system. And I think this is the primary thing that makes supporting these different from serving jobs is the data flow. It's a loosely coupled architecture in contrast to a serving system where you give a request and the response is served directly back to the sender. So tracing data through a system is different than just a distributed trace of an RPC. And this can lead to difficulties in debugging if proper instrumentation isn't in place. Pipelines and serving jobs may both call out to dependent services as they are transforming data or processing a request. So that's the same. Compared to user-facing RPC, processing can take extended lengths of time, like minutes or hours, instead of seconds or milliseconds. And since the input of a pipeline is often persisted and not subject to the RPC deadlines, the stage can be retried again and again, say, for example, if a pipeline fails. And if the pipeline does fail, it may need to start all the way from the beginning if it has not checkpointed where it left off or output partial progress. And pipelines have state. I think I mentioned this before. It's often persisted as intermediate output between pipeline stages. And the state can dictate what can be done in the next stage, and it can also cause a lot of errors when one stage or pipeline is expecting something different than what it's been given. So in the data processing space, there's been a shift towards more real-time systems due in part to increasing user demands on latency or freshness of data. And the streaming data processing model is particularly well-suited to low latency data processing pipeline if your users need real-time data because it's processing data as soon as it comes into the system. So as soon as the input is available, whether this is some sort of user event, the pipeline picks it up, does a transformation on it, and outputs it right away. In the batch mode, you kind of wait for all the data to accumulate, or maybe this is some sort of periodically scheduled job once a day, and you process you read all the input, you process it, and you write all the output all at once. Sometimes batch is more efficient than streaming because you only spin up like the workers and resources that you need and use them and then turn it off again. Streaming, you'll have long-lived jobs and they'll be continually processing data as it comes in. But if the data itself is more periodic than streaming, because even if you have the streaming pipeline, it doesn't mean your input is always constant, then you may have a lot of idle resources lying around. And depending on how large these is, it could become an issue to your bottom line. And you may need to look at different techniques like auto-scaling or turning down the worker pool when they aren't busy. This is a real pipeline system diagram of a large system within Google. I put it here just to highlight how, and this is more simple than I think the iteration before, but how complex pipeline stages can be. Input of one is output of another, but not only that, certain stages can have many different input sources. They can do re-indexing, aggregation, joins, and I put the pictures of the users on either side because that, like, you could call this one thing a pipeline. As far as the user is concerned, they generate some type of event and it's processed, and then they get it statistics about it on the other end. A variety of things happen in the middle, as you can see, including the yellow boxes are configs, like reading pipeline configs. Green is various data stores, not all in the same format. And actually, some of the blue boxes are serving jobs as well as pipelines. I just didn't get a chance to color code them. Okay, so now we kind of have what a pipeline is. set in context. It's just a variety, it can be a variety of different use cases and complex. But despite all the complexity and variation within pipelines, I'd claim that you can boil it down to two main failure modes. An incident response for them can be quite similar, actually, throughout. In the first failure mode, a pipeline is stuck. So for some reason, the output is not there at the end when it's expected. Perhaps no forward or slow forward progress is being made. Maybe most of the data is done being processed, but some stragglers still remain. Downstream pipelines that may be waiting on this output data may wait indefinitely to consume the data. In fact, they probably should wait rather than processing state that is incomplete or missing. And downstream serving jobs, if it's waiting on the data to serve it to users, may start serving stale or incomplete or even missing data to the user. So when you're paged and you realize it's your pipeline that's slow, you need to figure out how to get it going again, possibly how to speed it up to finish as quickly as possible. So to do this, you'll be hoping your past self instrumented the pipeline with monitoring and visualization tools, or that you chose a pipeline technology that already had these built in. That's perhaps even better. Well, actually, that is even better, because then you don't have to support them. To debug the issue, some things you're looking for in a tool is to be able to inspect where the pipeline is stuck. So is the input available? Is the output, are you having issues generating output? Like, is the storage throttled or in pushback? Are RPCs to dependent services during your transformation or other things like that going wrong, or are there worker failures? Is the transformation itself taking too long or causing errors? Is the issue due to a subset of data, or is it widespread? So exposing task ages, like where a task works on a single work item within the pipeline, exposing the ages of processing each task, the sizes of their input and output data, and the completion times or progress as distributions can help identify these issues. Being able to trace an individual work item through the system can also be key for finding errors, like where in the pipeline are things getting stuck. And if it is an issue for just a handful of tasks or users, like if it's not the entire pipeline that's stuck but a few, you'll want to be able to link back with that trace to, like, what does this mean from like the business side of things? Is it just one user or one account that is particularly large? Like how many users are actually affected? Because that's another thing, is when the pipeline is stuck or when things are failing, translating from like the unit of work back to like the user is also important. That's all to say there. Because now I'll talk about some kind of things you might do to speed the pipeline up when you're on call, and what you might need to see to do that. So first, don't forget to notify your downstream, First, don't forget to notify your downstream consumers or output that the user data is delayed. So let's say first scenario, you found a lot of worker failures, stack traces and logs indicate the pipeline's hitting a new piece of code, and errors line up with the last binary release. So you need to roll back. If you flag protected the feature, you can just flip a flag. If not, you roll back the binary, and hopefully nobody depends on the new feature, and hopefully the state that you've introduced with that new feature is backwards compatible. So we generally recommend when you turn on a new feature or introduce something new to your pipeline, don't use it until the next release in case you have to roll it back. So the next one is about dependencies. So let's say you found a high error rate and latency from an RPC to one of your dependent services. In this case, we'll say it's a storage system. It's in pushback. It's not accepting any writes. You need to kick off debugging that part of the system. Maybe you need to change your access patterns, or maybe it's an issue with their system, and you should see if they're reporting some outage. Another dependency is say you don't have any input data. Check. You need to so in these kind of loosely coupled systems, you need to know what step comes before this one, so you're able to go pull up that stage of the pipeline and see what's wrong with it as you identify where things are stuck. Okay, next category is more resources. So let's say the input is available, processing is going fine, but still the input is building up. You're not processing it as fast as it's coming in. It's not a performance regression because you see task processing times are similar from this release to the last. So one thing you can do is increase the number of worker resources. So sometimes throwing more workers at this problem or giving it more resources will help it catch up. But that's not always the case, depending on if the storage was in backup pushback or one of the other things we suggested. And an important thing to consider also about when you increase one set of resources, if the number of workers was a bottleneck in the pipeline, increasing the workers may now put extra load on your underlying storage systems or the servers that this pipeline calls out to. And depending on if those have proper load shedding and isolation, which we'll get to in the next point, it could actually take down some other more important job. So we've definitely seen all of these happen, by the way. Okay, next one, isolation. So you notice that the workers, you increase the number of workers to keep up with the load. Actually, in this case, you have a pipeline that's being slow, and you don't know why. But then you check to see, you find that it's a bottleneck in one of your the services you're calling out to at the storage system. And then you look and see that all of a sudden there's been a huge resource usage increase of this. So there's no longer any resources left for your really important pipeline to keep up. So at this point, you need to be able to see, oh, well, here's the spike in resource usage. What job or maybe other pipeline or system all of a sudden started using that? So both the ability to see which systems are incurring the load on another system, as well as, even better is if you have proper load shedding in this case, or quality of service instrumented, so the higher priority items and pipelines are processed before the others. This can, and sometimes in pipelines, can be implemented as separate queues, where even at the worker level, you maybe only say, pick up the tasks in the higher priority queue first. And sometimes storage systems themselves have quality of service that you can set differently on different jobs. Another one is outlier work items. So let's say you found just a few tasks that are slow processing large work items, and you need to find what makes them so big. It could be, and in this case, you see that, oh, there's a bunch of spam data. And in some cases, maybe things need filtering to achieve both a better quality, but also when there's too much extra data, identifying that it's not just organic growth, that it's some other type of load, and being able to address that is key. Okay, and lastly, maybe there's a region-wide issue that's causing the slowness of your pipeline. Say if your pipeline is just not making any progress, and you notice that many other of your jobs in that region are also not doing well, and there's an outage. You could wait for the region to become available again, or if you've structured your pipeline to be multi-homed in separate regions, you may be able to fail over directly to another, even automatically, without losing state. So if this applies to your use case, feel free to come talk to me after. But OK, so getting to the second case. So in other case, if the pipeline is, the next failure mode is the output of bad data. So the definition of bad in this case is deviation from the expected data when the given input is processed. Knowing what is expected is actually a very hard problem to know ahead of time or in real time. In the absence of knowing the correct results, you can curate a set of, say, golden data and use black box monitoring to check that the output from a known input matches what the known results are going to be flowing through the system. And if you've been alerted to a possible data issue, you need to quickly figure out where the problem lies, just like when the pipeline was stuck. You need to quickly inspect to see where the issue is introduced. It could be in a new pipeline binary or with a new pipeline config. I don't know, say like a feature that doubles the values you expect, or you didn't want to turn on deletion for a certain user. Or maybe like you're getting bad input from upstream or duplicate input and your pipeline is not idempotent, meaning that if it processes the same thing again, it won't produce the same results. So whatever the reason is, the output is wrong, users will be unhappy. Need to fix it. And fixing the data is well, both like having bad data is like really bad for the users, and fixing it can take quite a long time, depending on the nature of this outage. So it's really good to avoid. But if the issue is due to like a bad binary or config, you roll back, you stop the bleeding, like stop introducing the bad data as quickly as possible. Communication is really key in bad data, just like in stuck pipelines, to notify the people that depend on this data and or the users that like something might be going wrong. So once you've confirmed you're no longer introducing bad data, you need to repair the data. OK, we'll contact dependencies. Oh, and one other thing about the dependencies I wanted to mention is that sometimes your input data is just bad, and you're propagating this bad data through the system. And it might even be a different team that owns this input or some other thing outside of your scope. So you need to be able to talk with that other service, or maybe it's just a server that you yourself aren't that familiar with and you need to debug it. So having consistent tools and the communication is really important in these loosely coupled systems. Now on to restores. If, say, there's a lot of missing data or a widespread data issue, and you'll probably hope that you have a backup and that you can restore it, and that it doesn't take too long. Practicing this is important, and there's so much you can say about this. And there's actually a talk by Christine Bennett on Friday, who's back there. So I'll point you to that talk to learn, to go dive more in depth here. And the, oh yeah, another thing, in addition, maybe as an alternative to restoring from data, or if restore is not possible, either, well, hopefully your restore works, but like in the case where maybe you've generated completely new data, it hasn't been backed up yet, it's new, it's just wrong, you might need to reprocess it from the beginning again. How many here have done a reprocessing of their data? Okay, and does it take longer than you would like? Laughter, yeah. So this is like, yeah, it can take a long time. It can also be error prone. Automating this is an option, you know, depending, and also like if you have, let's see, if it's only like a subset of users that are affected, if you do automate it or you have a reprocessing system, you can save a lot of resources potentially by instrumenting those jobs to like take a flag of just the affected users. Let's see, I think those are all my tips. So. Users will be affected by pipeline failures, or at least distant parts of your systems may be affected in unpredictable ways. So this is something you want to manage. Like any disease, you don't want it to linger. too long undetected because it can take a long time to catch up, and preparing data can be a long, involved process. So that brings us to alerting and pipeline SLOs. So in the server-side world, we'd expect every request to succeed in a timely manner and have an error budget for failure. So in pipelines, we expect every bit of data to be processed in a timely manner, and we have an error budget for failure. When a server is unhealthy, the user may see timeouts or errors in the responses, and when a pipeline is unhealthy, the user will not see the output data or will get the wrong results. In server side, issues of correctness may be largely overlooked. Do the responses being served contain the information user expects? But in pipelines, data correctness is arguably the responsibility of the pipeline, since it's doing the actual data transformation itself. Hopefully by now I've motivated you that you need pipeline SLOs. Well, that's what this section is. You need pipeline SLOs, so we're going to go through a couple examples and maybe pick them apart for why they may or may not work as well as others. The pipeline has not completed successfully for more than 2 hours. So what's wrong with this measure? It doesn't capture the, it only alerts after there is an issue. So what if it's been 2 hours and no progress is being made? Like none, like you haven't processed anything. But if you have a target that the job must complete in like 2.5 hours, good luck getting it to finish in time if it normally takes 2 hours. So it's very, in this case, you may be alerting yourself past a point where you can possibly recover. And then if you try to correct it and bring that down to 1 hour, well, then you may actually be over-alerting yourself, because sometimes it doesn't take that long to process. So the next one we'll say is the 95th percentile of task age is less than 10 minutes. So this is like an internal measure of like how old the units of data within your system are when they're being processed. This is good in a way. It closely resembles the latency of a system, like latency of RPCs. But again, it's not necessarily what the user expects themselves. A task doesn't necessarily involve to like what the user thinks of as their data coming in one side and out the other. And it also doesn't represent the age of the input that could be piling up. So the unprocessed data. This is only an age of like the data that's within the system. How old is that? So then you might do one that's the 95th percentile of unprocessed data is less than 10 minutes. So this captures both input that your pipeline jobs haven't started consuming yet, processing yet, as well as anything that's being processed and not already output. So this is getting better. And still, though, with 95th percentile, you might still need an additional SLO for completeness or correctness, depending on your use case, to ensure that all data is in fact processed at some point. So for data correctness, like I said, data correctness can be hard to measure. And then for the measurements, you might find yourself making kind of going to cause-based alerts for your SLIs. So something like more than 2% of non-retriable errors when processing data. This is a cause of bad. This can be a cause of bad data because it's like dropped, like data that you're really dropping. So it could like necessarily require user intervention. So it's not a bad alert, but it's also not exactly monitoring on the entire system, because you could find yourself having 20 or 100 of these different causes, and you're still not going to get all of the causes. Then I've also seen some measurements that are more like this, that are more retrospective. So so say there's a billing pipeline. Like after 1 week from sending a billing report, the invoice will not vary by more than 0.05%. In this case, you're not alerted before an issue happens, but you can still use your SLO as an error budget for tracking when the system is stable enough. And let's see, also just to, for data correctness, this isn't exactly alert or SLO, but just want to cover it since it's quite important to have, and something I think SRE should be lobbying for, is to have end-to-end testing with golden data during the development process. So this is something that, like, even before the jobs run in production, part of the validation process should actually look at correctness. So next, preventing outages. So here I think we dive a bit into safe releases, cover things like canarying, incremental rollout, and some design. So what can SRE do during like consulting or just like during the, I guess, before incident response and monitoring? So first thing is that I'll cover is the pipeline canary. The goal of a canary is to validate the new pipeline on real traffic before pushing it to production and making it live. This can be, so the name comes from the practice of sending a live canary into a coal mine to see if it's safe for humans to enter. Canarying, there's also a talk on canarying in like a couple hours by Shepon D. So to learn more about this, I think for serving, and maybe you cover a bit of pipelines, go to that. So canarying a pipeline is something that some teams have adopted, especially if they have had many issues with performance regression, data issues not caught early on, and in particularly not caught until you actually run it on real data, like real traffic. So it's something we're advocating for even more widely in an automated fashion, because deciding automatically whether a release is good by comparing key metrics like the SLOs and measurements we described in the previous session is less error-prone than just letting a human decide these. And let's see. So one way you can canary a pipeline is to run the pipeline binaries side by side in production and compare key indicators of health, like the previous section. The canary pipeline reads the same exact input as the production pipeline, but it doesn't output data where serving jobs or the other consumers are going to see it. You compare the error rates and things like that. And then at some point after validation occurs, it can be switched over. So another alternative, if you don't have it instrumented in a way where you can run them both on the same real production traffic, is to have a pre-production environment which simulates production as closely as possible. So perhaps you've just take a sample of your production data and put it into pre-prod and run the whole pipeline there. You can still validate it on a lot of your same service level objectives. So in either case, the pipeline can take a long time to complete. So the canary itself can be quite long. It can take hours, say, for a pipeline to run end to end. So you can, but having something, even if you have to wait for the whole day for the pipeline to run, it can still be a good technique for driving towards faster releases that are safer, because for pipelines, I don't know all of your experience, but how many have, when you release pipeline jobs, do you do new releases and features, say more than I don't know, or do you do weekly releases or less than weekly release? How many do a release a week for a pipeline? Okay, how about once a month? Longer? Yeah, or how many do daily releases? Okay, so actually quite a widespread. Okay, the next thing is incremental rollout. So in this case, if you have a new pipeline or feature launch, you can actually do a percentage rollout where maybe you hash the data based on a user key to get a percent. You start with just loading the new jobs and then go up to 1%. 10% at some of these checkpoints, you verify how many resources it's using and if you're getting any sort of issues on the real production traffic. So this can be useful for capacity planning, and just like since pipelines, it is hard sometimes when you're introducing new features to see how that state is going to affect all the different systems. Isolating this down to just like a smaller percentage at first and then rolling out can minimize the impact if something does go wrong. But in the case of like large-scale data migrations, you may find it simpler to still run two stacks side by side and simply do a switch over at the end. But this is at a trade-off of increased resource usage. So design for outlier data. There are three things I want you to take away from this in terms of design. Well, this is first, just to describe this picture, it's a heat map distribution of task completion time. You can just see how the axis 12 hours, there are some tasks that take 10 to 12 hours to complete, but most really are done in like 10 minutes or less. When you have tasks that take a long time, it can actually slow down your whole pipeline. If it's implemented as like a batch job where you have to complete all of the output before the next downstream one can process, then it can actually just stall until the longest data is done processing before the next one can complete. Switching to streaming can help because achieve lower latency, at least for the majority of requests, because as soon as the short tasks finish, that data can unblock the downstream pipeline from processing that set of output as their input. And when you do notice that you have outlier tasks, consider the way you shard these. Is there a way to make the units of work more even? And lastly, consider the storage format of the intermediate data. So writes and reads to input and output can vary dramatically depending on the workload. If you have a date and an account user ID in your storage key and have some very large users, then you'll get much different patterns whether you put the account ID before the date or vice versa. So in conclusion, let's see. Pipelines are loosely coupled systems, and part of this is what makes them different from RPC serving jobs and difficult to instrument with tools. You have two failure modes. They either get stuck, data is stale, or data is corrupt. And there are ways to do pipeline SLOs where you can measure and be alerted if you're not meeting your goals for data freshness or correctness. And safe releases and a tailored design to your use case, your business use case, can prevent outages and minimize impact. So with that, I just want to give a thanks to the Pipeline Working Group at Google. The other people that wrote part of the SRE workbook on data processing pipelines and reviewed, and many folks within Google that did work on pipelines and helped with the content of this talk. So yeah, and that's it. Thanks.